Hey everybody, how's it going? So last time we looked at some LSTM time series forecasting, which is extremely essential, very important video, and if you haven't looked at that one and you're trying to watch this video, I'd highly recommend checking that out. I'm going to link it up above here. You can click that card. And so this is part two, where last time we were looking at predicting the temperature, and although I was a little bit lazy on labeling the graphs here, one of these two is the predicted temperature over time, and the other is the actual temperature, and you can see the predictions are very close. What it actually is each of these time steps here, these are hours. So we use the previous 5 hours to try and predict the next hour. And we can bump up that what we call window of information. Say we could make it the last 7 hours of temperature data and try to predict the next hour and so on. Okay, so we ended with this graph, and that was our test predictions and compared to our actuals. And it's awesome. Here's our pandas data frame that shows all of the data that was used to make that, the predictions and the actuals. We print that there. Now, there's no problem with this, actually. It's great. There's a lot more to do in time series, though, where I'm not even going to cover it all in this video. But something that you definitely might want to do is use more variables to help predict, because, often, in neural networks or whatever type of model, we don't generally just look at one type of variable. Technically, we're looking at 5 data points or 5 different values to use our prediction or to make a prediction. We're using the last 5 hours of temperature data, except there's no reason we can't just look at temperature. We can look at all these other variables. And if you recall, we have a bunch of them. If I scroll to the very top here, we have all of this information, okay? This is pressure. We are using temperature just to predict temperature. So we could use pressure to help predict the temperature and all of these other stuff if we wanted to, although we're actually not going to do that. Something else that we didn't even consider was using the actual time itself as a variable. And you might think like, okay, time, it's a timestamp. Why is that important? Well, actually, we have a lot of periodicity here. And if we were to graph it out over time, and in fact, sorry, I hit my computer there. If we do graph out the temperature over the years, and we did that, we can see a very obvious relationship here. It goes up and down like this. And if you think about that, that makes sense for the temperature, and it would for many other variables as well, where it's probably going to get hotter in the summer, depending on where you are, and assuming you have a summer, like most places do. And yeah, very interesting. So over years, we have this pattern like that. And also there's another pattern we didn't even think about, or maybe you did, is, well, okay, temperature. We know that in each day, it's generally hotter in the middle of the day. And I'm not sure if this is true for every location, but I assume it is. It's generally hottest in like the middle of the afternoon or so. And then it's colder at nights and colder in the morning. And it goes up and down like that in the same kind of way it does over years. So we can use that information, and that all actually comes from just what time it is here, from that timestamp. Although it takes a little bit, it looked like I was scrolling forever there. It takes a little bit of a transformation to get the something useful out of this. We're actually going to be translating it to seconds, just the number of seconds since some certain time. And after that, we'll do some sine and cosine transformation, which I don't really want to talk about too much. But the point is that we can use that sort of periodicity, or just graphically, it makes sense if you look like that, as variables as well. And including something like maybe the pressure as well, just to show we can use other variables here as well. And also, there's no reason that we have to predict one variable as well. Like, there's no need, well, if you wanted to predict just temperature, that's great. Except, why not predict the pressure at the same time? If we're trying to make a forecasting model for the future on climate, I don't know, why can't we just predict pressure? We totally can. And it turns out we can do it accurately. Okay, so there's all of that to consider, as well as something we haven't talked about is basically LSTM, and I believe I mentioned GRU last time. I'm not sure if I got to that. But basically, these recurrent neural networks are generally used or thought of as the go-to for forecasting stuff and predicting time series data. They're very common in natural language processing because they are time series as well. And so actually, there's not the only model that you can use. We have these things called convolutional neural networks, which people often associate with two-dimensional, meaning for pictures, goes through a picture, except that doesn't have to be true. We can do one-dimensional CNNs, which go across like that. Okay, so we didn't even really talk about that in the first video. All we did is make that one model, and then we showed the results of that model. And there they are, train, test, and val. And yeah, we're going to be making that today. In this next video, sorry, I'm just going to scroll to my other thing to make sure I'm in the right spot. Yeah, so I don't know why people don't really associate LSTMs or CNNs with forecasting as much as they should, because they're a lot lighter weight, as in we'll find out there's a lot less parameters that you have to learn here, which can make your model a lot faster, both in training and actually on inference time, how quickly it can predict as well. Okay, so a lot of interesting things to think about in this video, and we are going to cover a lot of them. So let's get started. Okay, at this point, I am definitely going to assume that you're somehow familiar with our code and what we did last time. So if you don't want to watch that and you want to try and follow along, that's okay, but I'm letting you know if you get confused, I would probably watch that one first. So to start, we're going to just kind of make a function that's I should say it before I start writing stuff and typing it wrong. We want to automate the predictions and the actuals and this graph all at the same time. So I'm just kind of taking a matrix of input and then making a data frame out of it and then plotting those columns. I want to do that all in one function. Probably should have done that last time, but it leaves a nice warm up for this time to remember what we were doing. So mean squared error, do that, import that as MSE. And we're going to define something called plot predictions 1, which is going to take a model in memory, not a model path, although that's an option too, model and x and y, and we'll say start and end indices. Okay, and we're just going to make those defaults to be start as 0 and end as 1, which is saying, okay, for this range, how much do you actually want to plot? And that's just for plotting. We're also going to use this MSE because I want to say the mean squared error, but I'm going to make that MSE over the entire set, but the plot is only over the indices specified. Okay, so we're going to get the predictions whoa, definitely not predictions. So predictions, or preds, whatever. Predictions is model.predict of x, and we're going to flatten that as before. This is really just copying from what's above, but putting it into a function. We're going to make a data frame out of this and do pd.dataFrame with those two columns. So that's data, we make it this dictionary. We set data equal to, it's going to be predictions, and predictions is going to be made up of predictions. And then actuals is going to be made up of actuals, which is y. Okay, that vector there. And then we're just going to plot these things, plt.plot, and then we're going to plot df sub. We're going to just plot both those columns, so we'll do predictions, that column, predictions, and yes. So how much do we actually want to plot? We only want to plot start to end. And we're just going to copy that, copy and paste that, because it's basically the same thing, but we're going to plot actuals as well. Okay, and we are going to return a couple things. We're going to return the data frame itself, as well as the mean squared error of the whole thing. So of actuals, that's going to be y actually, of y, and the predictions. Okay, so if we call this like so, if we do plot predictions, most notably we care about it on the test set of information. So we'll pass it model 1, our first model, and x test 1 and x or y test 1. And if you really recall, if you literally just did the other tutorial, you'll notice probably these variable names are ever so slightly different. I changed it just a little bit to match up with the rest of the code a little bit, but it shouldn't be anything crazy. You guys probably noticed that I spelled predictions wrong somewhere. Oh, no, I just have missing a 1 there. And plot predictions 1. There you go. So it makes, this is how it's going to plot a data frame when it's plotting other stuff as well, or show a data frame. Predictions and actuals, you can see they're very close, and the lines together are very close. Now again, I was pretty lazy on making the graph. As practice, you can absolutely make this a title, some x and y axes, and a legend to show which one is which, but I don't really care for the most part. I just want to show that they're pretty close to each other. That's the main point of this. Okay, so that was one thing I wanted to do, and we'll use that a couple times. Now we are going to make a convolutional neural network model. So we're basically just going to place the LSTM stuff, and so just to show you how easy this is, and actually it's how I would do it if I was making it from scratch as well, like we are, is I would take the model, because a lot of it's going to be largely the same. And I mean, you could play around with a lot of it by yourself. Feel free to do whatever you can with it, but we are going to turn the ones into twos. You're going to be seeing a lot of that today. I think we go up all the way to model 7, and you can optionally do more yourself. But here, so we're happy with 5 by 1. So recall that this is the time or the window length. We chose the last 5 hours, and the 1 here, well, one's often just for formality and for it being picky. It wants it to wrap it in a list saying, no, we're actually only doing one variable. Today we will be changing that, which is going to be exciting, but not yet. This is still our input, and it's only taking the temperature. That's the only variable. We're looking at it 5 times. Okay, so now the interesting part is we're going to replace LSTM with conv1d. And this is basically this sliding window thing. We slide this window around. So how many times do we want to slide this window? Or actually, how many windows? They're all going to be the same length, but how many windows do we want to slide across this is going to be this first number. We can stick with 64, that's fine. And kernel size, this is basically the size, and it's kind of weird, I'm using the term window twice here. The window for the input is length 5. We look at the last 5 hours, but then this window, we actually slide this network window across this thing. So you can think about it as this. Basically, if we choose length 2, so kernel size is 2, that means, and actually I guess I should use the word kernel instead of windows, it's less confusing, but people often say window here. This kernel, we slide it across, and it goes in order of the input for those 5 things. It says, okay, take these 2 things and turn it into 1. Take these 2 things, turn it to 1. And so if we're doing kernel size 2 with a window of 5, it's going to fit it into the first and second spot, second and third spot, third and fourth spot, fourth and fifth spot. That would be 4 locations that it could fit. And so it's actually going to turn this into so it's going to do that 64 times. So 64 by 4 is what it would turn that into. And then after that, we would need to do flatten, model2.add flatten, because we don't really want it in that this weird kind of 2-dimensional form. And we'll flatten it so that we can convert it to 8 ReLUs as before. And our summary is as follows. As we said, so it's going to take 5 by 1, and then it turns it into 4 by 64 or 64 by 4. Really this the same thing. And here, total parameters is 2,257. Isn't that just incredible? Like 2,257, if you recall, and we like low parameters for the most part. Of course, complexity in the model helps this be accurate, but it is way, way, way less parameters than this thing. 2,200 compared to 17,000, even though I chose 64 for both of those things. So that's incredible. GRU, which we'll actually see after as a replacement to LSTM, it's another recurrent neural network, and that one will have basically a balance between the CNN and and the LSTM. But anyways, for now, yeah, this is really, really good that it's low parameters, because it'll make the model run faster, easier to train, and many other things. Okay, so after we've made that model, we are going to, and I'm just going to I'm going to be copying from this other notebook. It's actually just copying from the same notebook as above. I just don't want to give you the headache of scrolling up and down. We're going to take the checkpoint code, that says CP2, which is kind of confusing because we haven't done a CP2 yet. So actually, let me just show you CP1, and we will translate that. We will convert that into CP1. So I just lied. I said I wasn't going to scroll up, and then I did. Really, all I'm doing here, and I'm going to be less picky about this later on because we're going to do it a bunch of times, but CP1, we're changing that to CP2. We're going to be saving model 2. Model2.compile, mean squared error is fine, optimizer with best learning rate is fine, and so on. Okay, compile that, and we're going to copy, and I'm just going to make this exactly as it is in my other notebook here. You can follow along pretty easily. Model2.fit, xtrain, ytrain, xval, yval, and make that the callbacks. So we'll fit this convolutional network model, and we can see it trains very quickly. The loss is going down as is expected and desired. Root mean squared error as well That's just the square root of it, and that's going to go for a little while. I don't really want to keep talking for the next minute or so. Okay, I'm back. So val loss, it went down to about 0.49, which is great. If we compare that to our earlier fit above, I try not to do this because I know it's a big headache to scroll up and down. Val loss, we got to about 4.87 before. Seems to be the best one. So that's pretty awesome. They were pretty much the same validation loss, very, very similar. But the complexity of this model is significantly decreased. Like this model would run a lot faster, most likely. So we would probably prefer that. Okay, so CNN is a great option to think about when forecasting. And just another warm up before we move on to more variables is replacing it all with GRU. And GRU stands for Gated Recurrent Unit. It's basically a simpler LSTM. And I just copied this code in because it's really the exact same thing as the LSTM code with model, I called it model 3. And same thing, takes the same input, except the LSTM is replaced with the word GRU. And our summary should look very similar, except here we have 13,000 parameters, which, as I said, is between the CNN and the LSTM. It's much more like the LSTM, though. It's fundamentally a lot more like the LSTM. Okay, so it's another recurrent neural network, and it's a decent option. The reason you might want to use it is because complexity is not always a good thing. It's it makes it heavier and a more slower to use model, as well as you're more prone to overfitting if you have more parameters and more complexity. So yeah, you might want to use GRU every now and then. So we're gonna again copy in this checkpoint 333, and that's fine. And I will train model 3 as well. I apologize for getting code out of midair, but it's really just you can follow along with it pretty easily if you've seen the other stuff, I think. So I'm gonna let that go, and yeah, loss is going down, down, down. Okay, so on epoch 10, we got the validation loss is about 0.48, pretty much the same as the other ones. And so again, we would prefer this model over the LSTM. We'd probably prefer the 1D-CNN most, actually, but we definitely prefer this over the LSTM because it's the same, pretty much the same accuracy and idea, but it's less parameters, and that's generally better if we could do that. Okay, so now we're going to move on to the idea, basically two ideas in one, is using multiple variables. So we only used temperature before. We looked at 5 steps of it, but we only used one temperature, or one variable. So we're going to use other variables, as well as this idea of translating a time into our timestamp into these usable signals. We're going to convert it to this one timestamp. We're actually going to get 4 columns of interesting, very important features out of it, which is the day signal, both day, sine, and cos signal. So there's 2 columns there: day sine, day cos, as well as year sine, and year cos. Okay, so to do this, we are first going to add a seconds column to the temperature. Firstly, so if I just remind you, we have temperature is this thing. And so we can make this new kind of data frame, which is temp df is equal to the pd.data frame out of temperature. And this is a little bit weird that we're just making a data frame with one column, which is kind of like a series, except there's a reason for it. So PD data frame like that. If you want to see what that is, it's just the same thing, but it's going to output it like it's a data frame because it's a data frame. Okay, so we have that, and we can see the index is still this timestamp here, which is going to be very useful. So we can add temp df sub seconds is equal to temp df dot index. Okay, that's that date timestamp date time column there. And we can map pd dot timestamp dot timestamp. Okay, and it's a little bit weird how that's what that does, but here, if we look at this column, this new column here, we have seconds, which looks like some really big value. It's 1.23 times 10 to the 9 or whatever, so very big value. And what is it, 1 billion, I guess? 1 billion seconds, I guess, if I have that right. And so why isn't this 0 seconds? Because this is the first time we have. Basically, it's actually not, this is not 0 seconds because this is all from some earlier timestamp, but it doesn't really matter. The point is the relative time, in that this is just some increasing value that's according to what the timestamp is. So you could, if you wanted to, subtract some value to get this down to 0, and then so on if that makes you feel better, but it doesn't really matter. Okay, so we have this now as seconds. And so this is a big stepping stone to converting this to day sine, day cos, and year sine, year cos signals. And I know if you haven't heard that before, you don't really know what I'm saying, but it doesn't really matter. So I'm going to plug in, well, actually, I'll write this out by hand just so you can get an idea for it. So we're going to get two numbers here, which is day and year. Basically the number of seconds that are in a day and the number of seconds that are in a year. So it's a lot. So day is going to be, well, we have 60 seconds in a minute and 60 minutes in an hour and 24 hours in a day. So 60 seconds in a minute, 60 minutes in an hour, 24 hours a day is the number of seconds we have in a day. And then if we have day, then we can just say year is equal to, and it turns out not to be 365, but more like 365.2425. It's kind of weird. That's what it is. Years in a, or days in a year. And so if we multiply that by the number of seconds that are in a day, this really should be called number of seconds in a day, but just day for short. So this would be number of seconds in a year. So it turns out we can use these signals to do something like temp df. We're going to add in a column here. We'll add first the day sine signal. And this is going to be equal to, well, something about sine, unsurprisingly. And not really going to explain how this works too much. Go ahead and read about it on your own if you want to. Basically, converting period signals into sine and time into sine and cosine signals. But we're going to add in, make this some sine thing where we do temp df sub seconds, that, and then we're going to multiply this by 2 times pi, or numpy.pi is stored in there, and then divide that by the number of seconds that are in a day. And it turns out that this gives you a nice sine signal. Sorry for the mess up there. I tried to do something off screen and it didn't work, so I'm just going to not do it. So anyways, that's our sine signal for the day. And we can look at it if you want with temp df. I actually ran that cell. And we can see here 0.25, 0.5, 0.7, 0.86, 0.96, and then it would start to go up, and then it would start to go down, and start to go up, and start to go down. So we turn that into this nice period signal, the sine signal. And we could do the same for a bunch of different things. So I'm just going to copy, the other three in there because I don't really see a point of writing them out for you. I'll explain it. Day cos is going to be the same except with cos and stick with day, and year sine is going to be the same except stick with sine and replace that with year, cos, year, and year. Okay, and if you wanted to output the whole data frame there, then here you can see they're very nice signals. And what's also nice about this is there's not going to be any other pre-processing. We actually didn't have to do any pre-processing before because we were only using one variable. We will have to do this now. But these are already in the type of range that we want. That's going to be, we're going to be very happy with that variable. So I'll stick with that and then just put .head so we don't have to have the whole thing in the notebook and carry on. Okay, so now that we have this basically in our new data frame here, we don't really want the seconds column because that's not going to be overly useful to us. You probably could include it in there, except there'd be some weird collinearity because it's based off of these signals. So let's not include that. We're going to do temp df is equal to temp df dot drop seconds, and then axis equals 1. And this reminds me, after I show this, that this is gone. Why actually weren't we happy with just the seconds column in general? Because this is some positive value. We could have done some pre-processing, like divide it by the max value, and then have values between 0 and 1 for each of these. Well, the reason is that there is this period data where basically as this time goes on, the temperature is going to go up and down and up and down and up and down, except this seconds column, this is just an ever increasing value. And so it should really wrap around where basically if you have a seconds that's equivalent to, that's very close to December, so say like late December, and you have a seconds amount that equates to, early January the next year. The seconds thing, this doesn't show that because it just shows the one number is bigger than the other. But really, they should have a very similar temperature value, and including the fact, more importantly, if we were to increase this 3-4 years in the future, well, this time in December, should this value for the column seconds or whatever we're using, this value should be very close to whatever it is in that December, because the point is that we're reflecting this kind of period data. What time is it in the year? Not how many seconds it is, what time is it in the year, or what time is it in the day. So here, today, it should be roughly similar to what it is 2 years in the future at the same time, or tomorrow at the same time. So we have to reflect these values somehow, and so we do that with this translating seconds into day sign, day cos, year sign, and year cos. So I hope that makes sense. The intuition is that this should wrap around, not be some ever-increasing value here. Okay, anyways, so we've got that, and let's move on. So the next thing we have to do is change our function that we used to make our window. So it made our inputs, basically turn it into, you know, these from this whole data frame into here's the 5, and also our labels as well. So we'd have our matrix of 5, 5, 5, 5, 5, and then the whole vector of corresponding outputs. So to make this output, or make this input-output pairs, we use this thing here, and we called it like that, and we'll see that soon. But anyways, going all the way down, sorry for the headache, we're going to copy that, and this is the idea. So just to recall, if you don't remember, the point was that each of these rows here, this is one row of information, and this is it. This is the answer, the next temperature. We have the temperature at 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, and 5 o'clock. We're going to use that to predict 6 o'clock. 2 o'clock, 3 o'clock, 4 o'clock, 5 o'clock, 6 o'clock. We're going to use that to predict 7 o'clock. So this is about turning the data frame into this function, into this format. That's what this is trying to do. This whole thing is X, and this whole thing is Y. So I'm going to get rid of that since we already have it. And now we're going to call this df to xy2. It's just for our next model here. And window size is equal to 5. Sure, that should be fine as well. But the difference here is that we are appending. So remember, actually, well, I just got rid of it. Yeah, actually, I want to keep that for now, because what we're using here is this is really T1, temperature at 1 o'clock, T2, T3, T4, T5. We're using that to predict T6 and T7 and T8. Or at least we're using this stuff to use 7 for predict 7, and this done to predict 8. So if this is all temperature data, I'll just add T's here. It's going to be the same idea, except instead of using just the temperatures, we're going to be adding these other columns. And assume, you know, we're going to be adding all 4 of these things, but I'm only going to show you one. Is this will be DS for day sign. So this we're going to want to put this here, day sign at 1 o'clock, and then day sign at 2 o'clock. And then so on. So I'll just copy that in. And I think this is worth the time. Skip ahead if you're annoyed by this, but I think it's worth for beginners to understand really the format of the data here. And once you get a hang for this, then you're really good to go. And so day sign at 1 o'clock, day sign at 2 o'clock, day sign at 3 o'clock, day sign at 4 o'clock, and day sign at 5 o'clock. And we're using that, you know, you could try to predict these other values, although that's kind of stupid because it's time and you know what the time is. But we could use that to predict whatever we want. We're only predicting temperature. We're going to use all this stuff to predict that at T6 and T7 and T8. So we're not going to change, that's what the label is. We're not going to change the label. It's going to still be the temperature. But here, we want to be adding in this row, this whole row of data, rather than just the list of the temperature. And here, this will be DS2, DS2, and this will be DS3, and so on and so on. It'll always be this number here. So in each of these, basically in each row, we want to have the following type of data. We want it to be a list, so 1 thing, 2 thing, 3 thing, 4 thing, 5 thing, where each value or each thing in there is a certain time step, and each item is itself a list where the first thing is the first variable of interest, the second thing is the second variable of interest, and we also have in here for all of them, we would have DC1, and here we'd have DC2, and here we'd have DC3, and we'd also have YS, year sign 1, and YS2. Okay, so we want to make this function, and I'll finally get rid of this. Hopefully that made sense, and if that was boring, I hope you skipped through it. Okay, let's write this function. So if you recall what we were doing, and I changed the window size here quickly to 6, because otherwise we would have 5, 1, 2, 3, 4, 5 variables, and a window size is 5 as well. I want those to be different values because I want to see how the shape turns out to be. And so we're going to be building this thing up, x and y, where x itself is going to be, its shape will be the number of training examples by the number of time steps that we're using times the number of variables that we're using. So if we recall what we were doing for the other function, we have for I in range, we iterate through the data frame with an index, and so we go through 1, and then 2, and then 3, and then 4. And in each of those, we actually grab this thing, df as numpy, I until I plus window size. So what that does is wherever we happen to be, wherever our starting point is, say our starting point happened to be here, I was 0, we would grab the next whatever piece of information, the next window size piece of information, we'd be left with basically this matrix thing here. That would be, this whole thing would be some cut of the matrix. And what it is that each of the rows is the time steps in order. And so what we can do, it turns out that we can actually just do, if we replace this with r, and it doesn't matter what variable name we use, but it's r, because each of these are a row of information. If we just grab this thing, that matrix, that split of the matrix that we want, and then we say, okay, row is the whole row for our information, and so our row is not going to be made up of just values, it's going to be made up of lists of values. And so here, this itself is going to be a list because it'll be full of these things. Okay, so it's basically R is going to be all of that. And then again, since this is a for loop in here, the next R is going to be all of that, and then all of that, and then all of that, and then all of that, and so on. So basically it makes it this whole thing, this list of lists here, where each of the inner lists is going to be one of these. Okay, a little bit confusing, and that's why I try to take this really slow and seriously, so you get how the input is made. We're going to each time append this row, and then label is going to, well, df is numpy, I plus window size, it's going to be the next, the corresponding output. And so, well, if this is a data frame here, this is a matrix, what that's going to be doing is actually grabbing, making it the row, the whole row itself. So what we need to do is translate that into the variable of interest that we want. And remember this, if we are wanting to forecast multiple variables, we could actually make this multiple piece of information, as we will later. But we want to make that sub-0 so that we append the right label on there, just the temperature value. So if we do this, we run that, and we grab, actually I'll just write it out for you, it's pretty easy. x2, y2, we're just doing 2's because switching with the 2's from before, or sticking with the 2's from before, sorry about that. X2, Y2 is going to be df2xy2, and that will be, we're going to pass in the df, which is, I believe, temp df, and the window size is 6 is totally fine. And then if we ask x2.shape, y2.shape, we should see, well, however many training examples. And for x2, we should have however many training examples by 6 by 5, because we're using 6 time steps and we're using 5 variables. And y2.shape, since we're just appending a value, it should be just the number of training examples is the value that we have. So here, x2.shape, y2.shape, 70,085, 6 by 5, 70,085. Again, just to make sure you know, number of training examples, number of time steps that we're using. Switch that to 4 if you want. I'll switch it to 6 after. Actually, there's no reason to switch it in there. Here, I'll just specify that the window size is 4. And here, now we're using 4 steps to predict the next information, the next value. And so we change the training number of examples a little bit. Okay, I'm going to stick with that with 6 and just actually remove that. So there's our matrix of input. I'm calling it a matrix. It's kind of weird. It's really a tensor. And our output as well. So now that we have that, we are going to really just copy the exact same thing that we have way above, and to not give you the headache, I'll just copy it itself. We're going to be splitting into train, test, and validation sets, and I'll remind you how that's being done. We're also calling these with 2's. So we're just saying x2 train is going to be this thing x2 up until 60,000, an arbitrarily picked number. But note that we're doing this in order, where we have train is chronologically in order. We're training on this, and then validation is in the future, and then test set is even in the future, like after that. And there's reasoning for that. And that reasoning is because, in practice, when we actually go to use this stuff, we don't have data in the future. So we want our model to be able to predict, future data better than it can predict past data. We don't really care about that very much. So anyways, x2 train is x2 up until 60,000, the first 60,000 rows. Y2 train is the first 60,000 information. Val is going to be 60,000, 65,000. Same for input and output. And test is going to be just the rest after this point, and the rest after this point for x and y. Okay, and if we see the shapes there, then we should see pretty much everything match. Or, well, yeah, everything match. Okay, so now we have to do something a little bit tricky and annoying. It's mostly just the syntax looks kind of weird since we're doing with tensors, but hopefully you'll be able to picture, and I'll try to explain it, is pre-processing for this type of data. So you'll notice that these are on the scale of, temperature. It's in Celsius. It's going, max like -40 or -30 up until like 30, 40, 50 or something like that. But that's still a much different scale than all of these other values. So we have to bring this temperature onto the same type of scale, like between -3 and 3 or so of these values. So how do we do that? We want to apply the same exact function, so with the same numbers doing the exact same thing to whether it's the training test, the validation set, or the test set. And so what we're going to use to make the function is the training set information. So we'll actually gather, and we're going to do just what's called, I always get them confused. It should be standardization, which is, no, I forget which one it is, honestly. The one where it makes a normal curve, whether it's standardization or normalization. And I think, it's standardization because it's making a standard normal distribution. And yeah, so for that, we need the training set mean and the training set standard deviation. And that's going to be just for the temperature because we only need to pre-process that column. We'll actually need to do it when we use other variables that are on different scales. We'll need to do it for those as well. But for this example, it's just going to be processing the temperature. Okay, now I want to do this through the NumPy way. So we're going to be getting the mean as well as the standard deviation of temp. So temp is temperature. Temp training mean is equal to the NumPy.mean of x2 train, and then I'll just write it and explain after colon 0. So try not to get too bogged down in this. I know it looks a little bit weird most likely, but remember the first dimension is going to be the number of examples in this. We want it to be made up of all of them, so I chose colon. The next one is the time steps. And we want all of the time steps because, we want the first hour and the second hour and the third hour and the fourth hour. And then of those spots, we have 5. And those are the 5 variables. Which variable do we want? We just want temperature. And I know it's a little bit weird, but if you really think about it, this will be all of the training, the temperature values that are in this whole thing is all of the values, the temperature values that are in the training set. And we get the mean of those, and that's what we want for making our pre-processing function. And we can do temp training standard deviation is equal to numpy.std of x2 train. It's going to be exactly the same thing. It's just the standard deviation of the same thing. x2 train colon 0. Okay, and now we can make our pre-process function based off of these values. And so we're going to define pre-process of x. So just any matrix, whether it's training test or validation, we're going to make that so that x colon 0. So we're going to set all of those values equal to itself minus the temp training mean that we calculated. So this is dividing, or sorry, that's not a minus, that's a 0. So first we're going to take all of our values and we're going to subtract the mean, and then we are going to divide it by the standard deviation. Temp training, STD. And that's how you would do that. And then if you want, you can return x here, but it is actually changing the thing that you passed in fundamentally. Okay, so that is our pre-processing, and now we can just go ahead and do this for each of our variables. Or sorry, what did I mess up there? Invalid syntax, define that. Oh, I messed the bracket there. Okay. So yeah, that's the mean, that's the standard deviation, that's how we make a preprocess function. We can just call preprocess on x2 train, preprocess on x2 val, and preprocess on x2 test. I think I said the wrong thing there. I'm not sure. Train, val, and test. And note that, remember, because I wrote it like this, and even though we're returning x and we're not using it, this is totally fine. So we do that, and we can see that that's our information right there. And it looks a little bit weird in that form, but I promise you that will be right. Now, okay, so we're going to make a model, which is really the exact same thing as above, the LSTM model, and I'm just going to copy it in for you and show the difference. The only difference is going to be the input layer. We're gonna have 6 instead of 5. This used to be 5 and 1, but now we're going to change this to 6 and 5 because we have 6 time steps and 5 variables of interest. And this happens to work just fine with our input. And I don't like how it's calling it 3 when we're calling it 4, but if we really wanted to change that, we could, but I don't remember how. Okay, and now above, we're going to do just exactly the same thing, so really don't worry about this. Another checkpoint and another compile, and we're just going to compile that. It works exactly the same way. We're going to fit it with the x2 data, so model4.fit with x2 train and y2 train, validation data of x2 val and y2 val, and epochs like so. And I'll show you at first that this is going to work. As we can see, the loss is going down very rapidly. And yeah, I'll talk to you at the end of the epochs. Well, it's at the end of the epochs, and actually, fantastically, we have a validation loss of 0.41. If you remember, we were getting about 0.48 or 0.49 with the other ones, so definitely a significant improvement with honestly not very much increase in the parameters. It was like 17,000 before, and now it's 18,500 or so. So not much more heavy-duty of a model, but a lot better. That is awesome. So now that we understand how to do that and we made a model, we are just going to use our plot predictions function. So I'm just going to write in plot predictions 1, model 4. Is that the right model? Yes, it is, model 4, with x2 test, our input and our output for the test. And here we go. It makes it we can see here the predictions compared to the actuals are very close, and our models, you can see it's predicting very, very close every single time. So even better than before. We can see this is the valid test loss, I guess, is 0.49, and really, really awesome. Okay, so we are pretty darn happy with that model. But I want to add one more thing in here, which is the pressure. Okay, so we're going to add in the pressure as well as the pressure as an output. Okay, so we're going to add in the pressure using as a predictive variable, but we're also going to try and predict it as well. So we're not just predicting temperature, we're going to predict the pressure at each time step as well. So they're going to be exactly the same as before, and that's why we're just kind of leveling this up more and more each time. Except instead of a 1 here, this is going to be a 2 for our model. We're going to be opening 2 things, and we are also going to be inputting. It'll be the same here, except we're going to be having another variable if we choose to use it as input. You really do want to use it as input, so we're going to put it there as well. And that's going to change our data set here a little bit. It's going to have another variable, but that's really it. And the output y2 used to be this long vector, and we just had vector the values comma, but now we're going to have comma 2 because we have 2 different ones. Okay, so knowing those changes, we're just going to go down and make them one at a time. So, okay, here we go. We're going to start with making that, basically adding that pressure to the data frame. So here we have p temp df. Sorry, that didn't type. Oh, I forgot to make this F11. Sorry about that. Okay, so we're going to do plot predictions. P temp df, which is just the pressure and temperature data frame in 1, is equal to the pd.concat. We're just going to be adding this column into our other data frame. We're going to be concatenating df, we'll just put it at the front here. df p brackets m bar happens to be what pressure is in the data frame all the way at the top. We're going to be concatenating that onto temp df, basically horizontally like this, or however you want to call it. Axis equals 1 makes it so that p temp df looks like this. Okay, it's just some code that really adds it in that the column there. Okay, so now if we have that, and I don't really like that, just show the head. It's too many information all at once. And now, so we're going to take that take that function as above, the window making one. We want to get our input and output pairs back. Well, we are going to modify that for our use case here. Now I am also going to change the window size, just because again we actually made it so that we would have had 6 variables, and that would be 6 by 6. So we're going to do 6 by or 7 by 6 instead, I guess. And so here, what actually changes in this function? Well, I'm going to call it 3 just to make that easy, to make our lives easier. And it's going to be very similar. So it's still going to be this bracket r for r in this. And it turns out the way we wrote this, it actually doesn't matter. We don't have to change that part at all, because, or the input part, because it's still going to be just append the row and then the row and then the row. So that's totally fine. The only thing here is that we want our output to be, we want to be appending a list where it's going to be, the list is going to be that sub the first thing and that sub the second thing, like that. And there's other ways you could write this a little bit cleaner, but this is totally fine like that. And append the label and make the array, and that's fine. Okay. So then if we get our input output pairs, I don't know why it's there. I'm going to press this button a bunch of times. I never have code blocks somehow. So here, and I know Krishna does that a lot as well. So 70,084 by 7 by 6. So number of information or number of training examples times the length of our window. We're using the last 7 hours to predict the next hour, and then 6 variables. And then our output is going to match up, except we're going to be predicting the temperature and pressure all at the same time. We are going to copy and paste this thing in here because it's really boring. It's just splitting it exactly the same way as train, test, and val. We could have wrote a function for this if we wanted to, but copy and paste is honestly fine for this kind of things. And all it is changing 2 to 3, and that's literally it. And the shapes are as follows: 7 training examples by window length by variables, and then training examples by the variables, which are training temperature and pressure. And it's like that for all of them. Now we're going to do something very similar, and we're actually just going to write this out, but it's mostly copy and paste from above for our pre-processing. And what we'll see shortly is that we actually want to, it's probably not that big of a deal, but we probably also want to pre-process our output as well, which has some complications. We'll see that, but it's not that big a deal. We want to pre-process our output as well, because now that if we look at the different values on temperature and pressure here, they're a lot different. Okay, so these values are a lot bigger than these, and our cost function or our network may be tempted to try to impact these errors a little bit more than these ones, because that's going to increase the value of the loss. So we do want to try and put these on the same type of scale, and we'll be able to restore that later with we'll call like post-processing to kind of restore these values from the predictions as well. Since we'll be telling it basically try to predict only like between -3 and 3 and -3 and 3, we want to be able to restore the actual prediction as well. Okay, so but for now we're going to just make up our pre-processing the input as well. For this, we're going to need pressure training mean. We'll just put a 3 there, is equal to the numpy.mean of x3 train sub : 0. Okay, so now that actually took over as the first column there, so that's why that's the 0. And we're going to copy that, but replace that with standard deviation with an STD, and that's fine. And that's going to be STD there. Okay, so we need those as well as the temperature, and I'm just going to copy and paste the temperature because that's not overly interesting. And yeah, okay, so we have both of those variables. Now we can write a new preprocess function. So how it looked was pretty much like this this before. Preprocess 3. Actually, no, I'll just write it out for you to make it clear. So define preprocess of we'll put a 3 there, of x. This is actually just pre-processing the input. Pre-process the 3x. It's going to do exactly the same thing, except to do that with both columns. So we want to do set all of those equal to itself like that. And then this is about the pressure. So we want to do P training mean 3, and divide that by P training, sorry, it's not showing up, P training STD3. And then we want to do exactly the same thing, except change the temperature column. So that's going to be 1 now, so 1 and 1, and this will be with temp 3. By the way, these sorry, 1 second. I'm acting like you're like talking to me. I'm talking to you. So I'm acting. Never mind. I don't know what I'm talking about. So basically, these values here, we didn't really have to gather them again. It's pretty much just the mean and the standard deviation of all the temperatures, which we already did that earlier, but it's a little bit cleaner if we have this here as well. And why do I feel like I messed something up? Yeah, I did. Peach, yeah, I figured that this was wrong. This is temp training mean 3, and this is temp training STD 3. Yeah, I was mixing them up there. Okay, so that's going to be our pre-processing functions for the input, as well as the input or the output. It's really going to be the same thing. And actually, I will just copy this one for you because it's exactly the same thing, except we're just setting it differently based off how the output looks. If we remember, the output looks like this, 5084 by 2, for example. So we're just going to say all the rows, and then the first column corresponds to the pressure. So we're going to minus those all by the pressure and divide by the mean of that, and then divide by the standard deviation. And the same thing for the temperature part. So that's a little bit weird how we're doing that. And it might not be totally necessary, but it's probably a good thing to do. Okay, a lot of talking, so it's getting a little bit sore. We want to pre-process the X3 information for all those. X3 train, val and test. This is going to be val. This is going to be test. Those are done. Okay, I pre-process all of those. I'm going to kill the output. We also want to pre-process the output. And just to do that quickly for you, it's going to be the same there. It's just pre-processing the train, the validation, and the test. Happy with that? No, we're not. I must have called it something different. Pre-process output is not defined. Pre-process output is, how is that not defined? Pre-process output. Did I not call that? I thought I called this. I'm just going to do this again because I don't quite know what happened there, because the name definitely looks the exact same. Pre-process output on Y. So I'm just going to run this stuff again because it gets a little bit weird if you do have to run it again. Where did it come from? Where did it go? Yeah, okay, so those variables look right. I'm going to recall that function, get that again, and make sure that that's ran. I'll pre-process it. And I will, oh, it's because pre-process, oh, I wasn't calling 3 there. That should be a 3. Yeah, sorry about this part. I like to leave it in there just to show you what happens if you do kind of mess something up a little bit. I don't like to pretend everything's totally pretty. So I will get that again. ptemp df is going to be that information on the function. Don't really need to do that. The x3 and y3, x3 train, and so on. This stuff, pre-process output. I really should call that 3 because that's a little bit weird without that. Okay, pre-process 3 and pre-process output 3 should definitely be defined here, and I'll be confused if that one doesn't work. Yes, that's totally fine. Okay, so sorry about that, and now let's make a new model. Now it's going to be basically the exact same thing as above, so I'm very happy copying and pasting because it's not too much effort. The input layer is going to be, again, the number of the window, so then the window I changed that to 7 to match that 7 that we were using. And the value here, that is going to be the number of variables, which is 6, as is correct, as we can see from this 6 here. Okay, so we have all of that, and yeah, that should make a model because we changed this, or off screen, I changed this to 2. So that's saying, okay, the first spot is going to be, say, for pressure, and the second spot is going to be for the temperature. Whew. Okay, so much talking, getting really tired. But that's what we're going to be doing. We are going to copy and paste the checkpoint here. CP5 is totally fine to match up with model 5. Sorry, I killed that. Model 5, there's our model. CP5, I don't know why these things are never coming in. And then model.fit. And luckily, I can take a little bit of a break because I've been talking so much, getting tired. And that's going to run with the X3 information right there as above. And just to make sure that that's working, yes, that seems to be going down. Okay, that is our Model 5, and we can see we have a very tiny validation loss. Now, recall that we did do this pre-processing on the output, which makes those values a lot smaller, and therefore make a lot smaller loss as well, which doesn't mean anything good or bad. It just means that the values are smaller. And the thing that we care about is that whether it's going up or down, and the validation loss, it starts out 0.04, 0.01, 0.081. It's clearly going down and down and down like the other ones were. And so we look pretty, I think we're pretty happy with that. Okay, now I want to make a function that's going to plot pretty much all of this stuff at once, and I do not want to write it out with you because I think you can just look at it and I will explain what it's doing. So here you go. I'm just going to copy and paste this function in here, which is, I'll explain what it does. So very similar to our other function earlier for plotting the results. It takes a model, some input, some output, and some start index and an end index. Okay, so we get the predictions like that, and that is going to be, the shape is going to be this matching like the Y here. It's going to be the first column is going to be all of the temperature or all of the pressure predictions, and the second column is going to be all of the temperature predictions. So we get the predictions, and then so pressure predictions is just the first column, temperature predictions is the second column, and the actuals, since we passed in Y, the pressure for the actuals is the first column, temperature actuals are the second column, and then we're just going to make all of this into the data frame. And we're going to plot all of this all at the same time, and then I'm also going to return the data frame for just start to end, and that's I'll show you why we choose to do that. So if I do this, plot predictions, and I called that with, sorry, I did that too quickly, model 5 and X3 test and Y3 test, so the input and the output there, we can see these numbers are very, very close. So for temperature, they're the predictions are very, very similar, which is great. For pressure, they're actually very close as well. So that's fantastic. And here's just the first 100 results here. And this also plots it for the first 100. We can see here the mapping is, again, I don't really know which one is the orange or blue or which one is the red and the green. But the point is that clearly one of the two is forecasting this stuff, and the other one is forecasting this stuff, and they're very close to each other. So to show the difference between temperature and pressure, temperature seems to go from 0.4 at the beginning and then 0.64, so 0.4 and then 0.64, so this is the temperature stuff, and our predictions are very close, and pressure, they're from negative 0.76 to negative 0.37, negative 0.7 and negative 0.37. Their predictions are very close as well. If you want to edit this to make again get a better function for graphing it, then absolutely by all means go ahead and do that. Okay, so that is our results, and they are very promising. But these are not numbers that we actually care about because we need to be able to undo this mapping. We can of course undo the mapping for the actuals because we have the actuals, but for the predictions, this is something where our model said, this is my guess, and we have to be able to completely undo this with some function mapping. And so we can do this by what's really called the inverse of, or the opposite of what our pre-processing is. It's kind of interesting. What we're going to call post-processing. Post-process, this is just going to be for the temperature, and I'm just calling this an array because it takes in really, you'll see how it works. It doesn't really matter what the shape of this thing is because it's just going to apply a function to that thing regardless of what it is. But so what I mean to say is it's a scalar operation. It's going to do it to every single element in the array. So I can just say array is equal to array times, and I'll explain this after, temp training mean 3, and then so we multiply that, and then we add temp sorry, that's not that first one. That should be standard deviation. STD3 plus temp training mean 3. Okay, and then the reason for that, and we'll return array. So note that this doesn't actually change this thing. This returns back a different one. So the reason, before we had a divide, and so we changed that. We do that first to do a multiplication, and then after that we do an add. This happens to be the exact inverse of that standardization function. It gets back our prediction. And so I can write the exact same thing, but for pressure, and that's just going to be like this. Postprocess P of our array is multiply the array by that P training standard deviation and that training mean as well. So we have those post-processed, and then really this exact function, I'll just show you how it's made so we can follow this. This exact function we have before for plotting our results, but we can do return the results, except with it post-processed. So we can put, we need to do this one. This is for the pressure. So we can do this post-process P, the pressure value there. We undo that. I'm going to copy that. I'll be writing that a lot. Post-process, this is going to be temp, like that. Okay, so we call that function there. And post-process P of the first one there. And then post-process P of the temperature as well. Sorry, that's not right. Temp. Okay, so that's doing exactly the same thing, and I'm sure you don't have to write that much code. There's a better way to do this, but that's just going to return it post-processed. So that if we were to call it, and actually let me just, this returns the data frame, and yeah, actually we might play around with this shortly, but we'll call it like this: post-processed df is equal to plot predictions to, oh, I remember why. Yeah, we're going to be switching this up. Plot predictions to, and this is going to take in model 5, x3 test, and y3 test. Okay, and then post, actually, sorry, yeah, it's fine. This returns the df, so that's why I'm kind of just grabbing the df. And there's a bigger reason for why I'm doing this shortly. So this thing, and it plots this, you can't even tell that there's 4 curves here. It looks like there's just 2. Actually, maybe you can see it a tiny little bit that there's some blue down there. But yeah, so they're so close, and when we scale it like this to what they actually are, they end up to be so close to each other. And so because of this, we really can't graph them in the same plot. At least I don't know a nice, pretty way to do that off by hand. So we're going to just split them off, really. And I'm going to do this quickly for you because I don't think it's too relevant. Basically, if we did, this is how we would do this. Since we grabbed post-processed df here, I can do, say, start end equal to 0, 100. We need to take this out of the function because we're not doing it in the function anymore. Just with the df, temperature predictions and actuals from start to end, we could plot those. And there's that. So that's just for pressure. And that's just for temperature. And we can do this just for the pressure as well with plotting the pressure. And it's nice how it knows this really crazy jaggedy pattern, which is incredible. So that is mostly the end here. And it's really the end if you want it to be, but I encourage you to stay for another just a few minutes where I'm going to show you some interesting things about time series and LSTMs. So with the LSTM model, if we take the exact same model as before, let me just grab model 5. Model 5, where are you? So much code here. Model 5. Okay. There's something interesting we can do to increase the complexity of the model if we wanted to, and you'll see if people do this a lot. Why can I not? I never have these code blocks. I don't know why. So here, we have model 5, but also quickly switch it to model 6. I'm not actually going to fully train it. I'm just going to train it up until the point that shows you it works. Here we have LSTM 64. If you wanted to actually do this weird kind of chain, it makes this kind of like a square model almost. Basically, you pass things upward and then upward and then upward rather than just kind of recurrent through this thing. And I know it's kind of hard to picture if you're not super knowledgeable about this stuff. But basically, and just to do it in code, we can do model6.add another LSTM, and we can do this, say 32 of them. It actually didn't really matter the value too much. return sequences equals true. And this makes sense roughly because you know that this LSTM, it takes a sequence, it takes a time series. And so if we feed it in, if it says, hey, return the sequences, and then feed it into this LSTM, it's basically passing this already processed and learnable LSTM here, passing that into this next one here, which is very interesting. That model would work. I'm not going to bother. Actually, sure. I will quickly just grab those. Actually, I'll grab it from my other notebook so that I don't have to bug you with this. So here, just model 6 checkpoint would be exactly the same thing, and that's totally fine. And no, it's not. Model 6 is not defined. I didn't click that. Now it's fine. Yes, there's the model. So 7 by 32 now, and 64. Okay, very interesting. More parameters for sure. A lot more parameters. It's a heavy model. 30,000 is definitely approaching a big model. Model 6 is defined now. There you go. There it is. We're going to fit that just to the point to show you that it's going to work. I don't really care about the accuracy, but I'm telling you it's probably going to be pretty darn high. Might overfit a little bit. That's quite possible, but it's going to work. And I'm not going to let you see that. Absolutely go for it if you want to check out my notebook. It is in the description like always. And model 7 is something else, which I'm just going to paste here for you, is takes in 7 by 6, and then conv1d 64 kernel size of 2. Let me show you something. Okay, if we go back up to, all the way up into our other convolutional model is here. Let me paste them side by side to show you the difference. Remember that why we were doing this is because the window was 5 and we were just using one variable. Well, here we just specify the input. You always got to do that anyway. The window is going to be 7 now with 6 variables, and then conv64. I guess I should also do an activation equals ReLU there. I don't know why I didn't have that earlier. Activation equals ReLU is pretty common, and yeah, so it is exactly the same thing, like exactly the same. You just specify that the input is going to look a little bit different, but it doesn't change the convolution part. This works totally fine. And what it does is kind of traces this, like, because we have, you can picture basically, it works on this matrix of input. And so we're going to be sliding, or each row is going to be a particular variable, pretty much. And it's a little bit tough to picture that way, so actually I wouldn't worry about it too much. Basically, you're sliding this window across multiple variables now. And this works as well, and that could be a lot later model. And as we'll see, I'll just let it do that. Also, we also changed the output, but that didn't have to. So here, it's still only 4,000 parameters, and it's totally happy with that. And again, just to prove that it's happy with that, I will quickly grab the compile code. CP7 is, I can put that right here, is actually fine. And fit that model, and it will work. It will be very happy with that. Okay, so pretty fantastic. Yeah, excellent job if you did get this far. I'm guaranteeing most people didn't get this far. It's a pretty tough, heavy duty video, but I hope you learned a lot along the way, and drop a thumbs up if you did get this far, please. Subscribe if you're not. I assume you are if you got this far, but if you're not, then definitely want to subscribe. And yeah, we're probably going to make one more time series video at some point. There's some other interesting stuff that we could look at, like forecasting more into the future all at once. There's more to it for sure. And I'll definitely at some point make a video for forecasting the stock market is a very common one. But temperature is pretty interesting too, and it teaches the nice LSTM idea, which is most important for jobs. Job market is just understanding how this forecasting input window is working and how you can make these models. This teaches that pretty well. So yeah, like, subscribe, and yeah, I'll see you in the next one.